Michael, this is one of the test beds I use here. It's just made out of one of my spare backplanes, one of the early versions of that, I guess. But I've got the memory board mounted in there, and I'm doing a little poking around with the scope, and I don't know what the delay ought to be, and I can't find anything on it on the internet between the trigger pulse and the delay to write in the memory chip. But I'm wired into the input pulse right here, and I programmed the Arduino to just sit there and generate pulses for me. And it's generating those at, let's see, it's at about 116 kilohertz. And as fast as a little Arduino will go, which gives me kind of a square wave, but the way I've got it hooked up here, there's a lot of stray capacitance and inductance interacting with it, but it's good enough, at least for this test. I wanted to find out how long that delay was taken from Brian's circuit. So I'm clipped onto the output of that to the write signal that goes to the chip here. So I got both the input and the output, and I got both channels working on the scope. So I'll show you what's coming up. The bottom trace is the trigger pulse. You can see it riding along here at high, 5 volts high, and then when I get a trigger pulse from the Arduino, it drops it to 0 volts. Well, that triggers Brian's delay circuit, which works all right. And there's the pulse coming out of Brian's delayed circuit. And I don't know if you can read the legends or not there, but I've got 200 nanoseconds per division. And I've got a suspicion that that's too much. And I'm missing the right cycle. The input pulses, and I'll try to measure that on a real board. But unless that input pulse holds for a while, for long enough time to hold the line driver chip active, why that pulse could very well miss the whole ball game, come flying along after we should be getting our right signal. And that's what I'm thinking. But again, I'm not sure. Now, the way to find out, I'm going to jury-rig the board to keep that line active like it was before all the time, and we'll see what happens. I kind of suspect then it's going to work, but I think that the chip is going in active. The line driver chip is going in active before the memory chip gets that right signal. But the delay circuit's working fine. As you can see, it's poking out let's slow it down a little bit here on the horizontal trace. You can see it's triggering on every downswing like it should. And when I move in closer, you can see that delay. Now we're at 100 nanoseconds per division. Let me move her over so she starts right on a division. And I got a little capacitance on that circuit, so that's not the best downhill pulse, but it should be sufficient. Goes close enough to 0 holds in there for 50 to 60 nanoseconds. We're now 100 nanoseconds per division, and you can see we got about 250 to 275 on the delay. Now I have to add it up here after a bit, but anyway, you can roughly see what's happening there. Now I've moved into a time division there, 50 nanoseconds. And if you can see the grids, let me shut off this overhead light. You can see the grids there if you count them from the dip in the input signal in yellow. 1, 2, 3, 4, 5, so that's 250, then about half of the next division. So that's right at 300 nanoseconds. I think that's a little too long. I think that's a little too long. What do you think? That's my take on it. If I change that timing constant there, I can shorten those up. And I may just end up doing that. Either increase or decrease the resistance, or put a variable resistor in the circuit, and go with that to see if I can get that thing working. That's a good idea, Dick. Give that a shot, buddy. All right, over and out.